All right, let's talk about a cosmic puzzle. A story about a planet that frankly shouldn't exist. It's a discovery that broke all the rules and forced scientists to rethink everything they thought they knew about how worlds are made. So get ready, because this is a detective story set 280 light years from home. So here's the central mystery, the question that started it all. Imagine you found a cannonball that floats. It makes no sense, right? Well, that's exactly the kind of contradiction astronomers were facing here. We have a planet that, by all logic, should be incredibly dense, but it's not. It's way too light. So what on earth is going on? Okay, let's meet our main character, a planet called TOI-561b. It's what we call a super-Earth, bigger than our own planet, but still rocky. And get this, it's orbiting a star that's about 10 billion years old. That's more than twice the age of our sun. This ancient world has a wild story to tell, and it all starts with one single, baffling observation. So here's where it gets really weird. When astronomers first measured TOI 561b, everything about its size told them it should be a super dense, heavy ball of rock. But the reality? It was completely different. Its density was shockingly low, as if it were puffy. It just didn't add up at all. And it's not just us saying this is weird. The lead researcher, Johanna Teskey, basically said the same thing. The team knew they were on to something huge. This anomalously low density was their first big clue that TOI 561b was hiding a massive secret. Now, let's just paint a picture of this place, because it is a world of absolute extremes. Its year, the time it takes to go around its star, is only 11 hours long. It's also tidally locked, which means one side is in a permanent, scorching daylight, while the other is in an endless, frozen night. And that star-facing side, it's so hot that the entire surface is just a giant, bubbling ocean of molten rock. In an environment like that, with a magma ocean getting blasted by intense radiation, any hint of an atmosphere should have been completely stripped away into space billions of years ago. A bare, dense rock is all that should be left. And yet the data, the numbers, were screaming that this planet was fluffy. The mystery just kept getting deeper. So that's the big question the scientist had to answer, right? If it's not just a solid chunk of rock, what else is there? What could possibly explain that low density in such an unbelievably hostile place? To find the answer, they needed a new set of eyes, a much, much bigger eye on the universe. And that's where our hero comes in, the James Webb Space Telescope. Its incredible power could give them the one piece of data they needed to finally crack this case. The mission was simple, but totally brilliant. Point Webb at this strange world and take its temperature. This was it. The moment of truth. This temperature reading would either confirm that the planet was a bare, superheated rock, or it would reveal something else entirely. So, after all that, what did Webb see? And the results were staggering. The models predicted that without an atmosphere, the surface should be a blistering 4,900 degrees Fahrenheit. But what Webb actually measured was only 3,200 degrees. Now, that's still insanely hot, but it's way, way cooler than it should be. This was the smoking gun. You see, that huge temperature drop could only point to one solution. Something was grabbing all that intense heat from the day side and moving it around to the cold night side, kind of like a global air conditioner. And that something had to be a thick, circulating atmosphere. The mystery of the low density was finally solved. But hold on a second. Solving one puzzle just created a brand new one. We already said that this kind of environment should absolutely destroy an atmosphere. So how could one possibly exist, let alone stick around for billions of years? Well, the answer wasn't in the sky above the planet, but in the molten rock below. Scientists came up with this really mind-blowing idea they call the magma ocean equilibrium theory. It suggests that the planet's atmosphere and its molten surface are locked in this incredible cosmic dance, a perfect give and take that keeps the whole system stable. So here's how it works. On one hand, you have the star's brutal radiation blasting gases away from the top of the atmosphere. But, and this is the key, at the same time, the roiling magma ocean below is constantly outgassing, releasing trapped gases from deep inside the planet. So as fast as the atmosphere is being stripped away, it's being refilled from below. It's this amazing, stable balance. And one of the researchers, Tim Lichtenberg, came up with the absolute perfect way to describe it. He said to think of TOI-561b as a wet lava ball. It's a world so full of these volatile gases that its molten surface is constantly feeding its own sky, keeping its atmosphere alive against all the odds. So why does solving the mystery of one weird little planet 280 light years away matter so much? Because this discovery completely redraws the map for where we can expect to find atmospheres out there in the universe. It basically tears up the old rulebook and throws it out the window. This changes our whole perspective. First off, we now know that even rocky planets in the most hostile star-blasted environments can somehow hold on to their atmospheres. Second, we've learned that a magma ocean isn't necessarily a planet killer. It can actually be an atmosphere sustainer. And that means, finally, that the number and types of planets where we should now be looking for atmospheres just got a whole lot bigger. And that really brings us to the final thought here. TOI-561b was the planet that shouldn't exist, a puzzle that seemed impossible. But by figuring it out, we've learned that the universe is so much more creative and so much more resilient than we ever gave it credit for. And it really makes you wonder, if a wet lava ball like this is out there, what other impossible worlds are just waiting for us to find them?